Hi everyone. So we are going to start with probability. This is the second chapter from the textbook. So a little bit of background on probability, right? So this area of probability has its origin in gambling. So the first attempt to define probability or to work in probability with some kind of mathematical rigor was done by Laplace in 1812. So this is a long time ago, but it's not that long ago, right? People were working in maybe some of the other areas from much earlier. So probability is relatively a new area. So Laplace, he gave the classical definition of probability, which is basically the number of ways, or he defined probability as the proportion of the number of favorable outcomes to the total number of all possible outcomes. So this is the definition that probably some of you are already aware of. So for example, if you were dealing with a deck of cards and you wanted to calculate probability that you draw a card randomly from the entire deck, and if you want to find out what is the probability that the card that you pick is black, so there are total 13 black cards, right, and total 52 cards, so probability that you draw a black card is 13 by 52, right? So it's the proportion of number of favorable outcomes to the total number of possible outcomes. So this definition was given by Laplace. However, you'll see that it's quite restrictive. It's not perfect, this definition. So for example, what happens if, so in terms of cards, there are only 52 cards, but what happens if the number of possible outcomes are infinite, right? Then this definition wouldn't work. If you had infinite number of possible outcomes, then and a finite number of favorable outcomes, then your probabilities would always be zero. So this definition is a bit problematic. It is useful for many practical purposes, though. So the mathematical theory, right, as it exists today, is being it's relatively new, like I mentioned, and this was basically the first serious work was done by Kolmogorov in 1933 in his work called as Foundations of the Theory of Probability. So Kolmogorov, he represented random events as sets, and probability he defined as a normed measure of these sets. So for example, if your set is, say, an interval from 0 to 1, then your measure is basically the length of that interval, which would be 1. If you are in higher dimensional spaces, right, if you have a cube, then you can calculate this measure would be just like a volume, right? So instead of defining it like Laplace did, he made the definition of probability more general. So probability has plenty of applications. Chances are, if you're attempting to do any kind of data analysis, even if you're trying to fit some kind of a model, you are going to encounter probability. So even if you're fitting a regression model, say your error is going to have some kind of a random distribution, that means it will have some kind of probability associated with it. Probability occurs in probably every data analysis that you might encounter. So it is used in it's used widely. It has applications in healthcare, finance, economics, agriculture, weather prediction, sports. These are only some of the areas. Like I said, if you're attempting to analyze anything, you will encounter probability, as long as the thing that you're analyzing is not deterministic, right? So let's see some of the applications in finance. So if any of you are from maybe a business school, or if you're interested in finance, you've probably heard these terms: asset pricing, factor models, portfolio optimization, derivatives evaluation techniques, estimation of and forecasting of time series. Okay, so I'm not going to go into details. These are just some keywords that I'm throwing at you, and to give you an idea of different applications or more specific applications of probability. In sports, you have, I don't know, pick any favorite player, say LeBron James. What are the chances of making 10 free throws in a row, right? A question of this sort can be answered using probability. We'll be able to answer this kind of question probably by the end of this chapter, right? Again, we can use concepts of probability to analyze games or to analyze different players. So you can review, so if you're looking at baseball pitchers or baseball hitters, you can look at their past records and you can see what and you can study their game, right? So you can find you can use probability to know which player is susceptible to what kind of games. Basically, you can use it to find out the weakness and the strengths of different players. It has applications in agriculture to study different kinds of factors that influence agricultural production, or even we can use it to measure contribution of agriculture production to the national growth, to the national product, that is the GDP. Like I said, these are some of the applications and there's many more. I just tried to throw some big ideas at you. So we'll start with set theory. So as I mentioned earlier, Kolmogorov, he defined random events as sets and he defined probability as measures on these sets. So any kind of, so a study of probability typically begins with study of sets. On this slide, we have some notations. So if we have a set A and if the set A contains 3 elements called as A1, A2, A3, then it's denoted in this fashion. So this curly bracket here indicates that this is a set containing 3 elements. Set A belongs to element A belongs to set A is written in this way. So this notation here is basically it's belongs to. It's a notation for belongs to. A universal set is a set of all things under consideration. So if I'm tossing a coin, then either I'm going to observe head or tail. So that's my universal set containing heads and tails. If I'm dealing with a deck of cards, then my universal set is a set of all of the cards, right? So this universal set varies from experiment to experiment or from situation to situation. However, it denotes all of the things under consideration. Typically, universal set is denoted by this letter S or this notation omega, okay? It's possible some other notations are used, but S and omega are commonly used to denote the idea of a universal set. Set A is contained in B is written in this way. A contained in B, A contains B. You flip this notation around, okay? A is contained in B or is equal to B. You put this line here, right? So this means A either is contained in B or it's possible that the two sets are equal. Similarly, you can have this also, okay? So this means either that A contains B or the two sets are equal. Empty set is denoted by phi, okay? So now we'll take a look at some of the operations that we can conduct on sets. So they're called as set operations. So the first one is union and is denoted by this notation. So AUB is basically set of all X. So again, familiarize yourself with this notation and this way of writing sets, okay? So A union B is a set containing all of my x's, all of the points, right? I'm using x to denote the points. This line means such that, So all of the points such that this point X all belongs to A or X belongs to B. So it's a set of all points that either belong to A or B. Or you can rephrase it this way. A union B contains all the elements that lie in at least one of the sets. It's possible, right? So either they lie in A or in B, or maybe in both of them. So in at least one of the sets. So you can depict it using Venn diagrams. Venn diagrams is a very good tool of visualizing set operations. So this rectangle here is the universal set, and I have this set A, I have this set B, and this blue area is basically A union B. The next operation is that of intersection, is denoted by this notation, and it's denoted, so A intersection B is a set of all elements X such that X belongs to A and X belongs to B. In other words, A intersection B contains all the elements that lie in both the set. So this is how it is depicted using Venn diagrams, right? All of the elements here lie both in A and in B. That's A intersection B. So another definition. So set A and B are mutually exclusive if their intersection is empty, right? So they have nothing in common. So if you were to depict this using Venn diagram, it would look like this. This is A and this is B. A, B. They have nothing in common, right? Then we come to the complement. Complement means basis. So complement of set A, so this A bar here is a complement of A, is a set of all elements X such that they do not belong in A, right? So it contains all of the elements that are not in A. Other notations to denote complements are this A prime or AC. Okay, so I'll switch between these three notations because chances are if you go to the internet to look for to search any information on sets, either of these three notations can be used. So A complement can be denoted either by A bar, A prime, or A complement. So in terms of Venn diagrams, again, this rectangle is a universal set. So remember, anytime I say that it contains elements that are not in A, right, but the element has to be in your universal set, right? It has to, it has to be in your universal set. So this is a rectangle, and this blue area is A complement. Okay, so next we come to set identities. So set identities are a bunch of relationships that that are followed between, or that connect these different operations together, and these are important. So so these set identities will play an important role in solving problems. So you should be familiar with them. Okay. So what is the first one? So this says that A can be written as A intersection B and union A intersection B complement. So how do I verify this? Okay, so Venn diagram is a good way to go about this. So let's see, I have this Venn diagram here. So this is A. What is this saying? That this set A can be decomposed in this two ways. So let's see what is A intersection B. So A intersection B is this. I'm going to have these lines, and A intersection B complement. So that is everything that occurs in A and does not occur in B. So it is this part. Okay. And now if I take the union of these two parts, I'm going to get this entirety of A. So this trick we will be using quite a bit in solving problems, okay? Especially when we do Bayes' theorem, this will come handy. So any set A can be decomposed in this fashion. Note that A intersection B, and so this set and this set are disjoint, right? So these two sets are disjoint. So any set A can be split into these two disjoint sets in this particular way. Okay, again, this is an important trick. The second one is saying we can do the same thing with B, right? We can split B in a similar way. So maybe I'll use a different color. So B can be split as A intersection B. Maybe I'll erase this first. So this is A intersection B and B intersection A complement. So again, we're doing the same thing that we did on A to B. So there is a whole host of set identities, right, which again is useful in solving problems. So this one says that you take a set A, then you take its complement, you take its complement again, you're back to the original set. So just see, so I'm not going to verify all of these identities. It's fairly simple to verify them. I'm going to leave it as an exercise. So this is set A. So A, right, this is A. A complement is everything that's outside this set. I don't know, maybe I'll use a different color, right? This whole thing is A complement. So the complement of this set again, right, you go back inside set A, right? So complement of this complement is back here, right? So this diagram looks a bit messy, but it's a fairly simple concept, right? So complement of a complement, you get the original set, okay? So this says that A union B or B union A. So if I reverse the order of the sets, it doesn't change, right? So this is pretty easy to see. Union of a set A with the universal set is the whole universal set. A union A complement, right? A union A complement is again the whole universal set. Union of the set with itself is the same set. A intersection B, again the same thing with intersections. A intersection B is the same as B intersection A. A intersection with an empty set, you intersect A with nothing, you're left with nothing, so it's empty. A intersection with S is A again. Intersection of two disjoint sets, that is A complement, right? A complement are disjoint, it's empty. If A is a subset of B, right? So let's see, this is my universal set. A is a subset of B, right? This is A, this is B, this is A, this is B, this is A. A union B is this whole thing outside B, and A intersection B is A, right? And then finally we come to this bunch of identities called as De Morgan's laws. De Morgan's laws are extremely important, right? So this says that complement of A union B, right, is A complement intersection B complement. And this says that complement of A intersection B is A complement union B complement. These are important identities, probably one of the more important ones on this slide. So make sure you use Venn diagrams to understand what is going on here. So the goal here is not to memorize these quantities, but to get a better idea or a better hang of these relations, to get a better understanding of these different set operations, okay? So again, you're not expected to memorize. However, these should be intuitively obvious to you. And once you play around with Venn diagrams a little bit, these will be clearer, okay? So here is an example. So this is an exercise in translating words to notations, okay? In mathematics, especially, in mathematics, statistics, whenever we're doing problem solving, or even if you're doing research for that matter, it is important to be able to translate words to mathematical notations and basically translate words to mathematics, okay? So that's what we're going to attempt here. So we have three sets, A, B, and C, and we'll try to write the expression for this, right? So A occurs but not B and not C, right? So A occurs, B doesn't occur, and also C doesn't occur. So take a moment, pause the video, and try and write this down in terms of set operations, right? B and C occur, right? But A doesn't occur, right? So let's see, maybe I'll do this one. So B and C occur, so that's B intersection C, but A doesn't occur. Intersection A complement, right? So see if you get the same one. So only one of A and C occur. At least one of A and C occur. So pause the video, try and write down these relations, translate these statements to set operations. And here's the solution, right? A occurs, not B, so that's B complement, and also not C, that's C complement, right? So all of these C are occurring, and therefore you have the intersection here. This I've already explained. This is an interesting one. So only one of A and C occur. So break it down. So there are two possibilities, right? So only one of the two are allowed to occur. So it's possible that A occurs and C doesn't occur. That's A occurs and C doesn't occur. So that's C complement. Or, so therefore, union. So whenever you find yourself thinking either this happens or that happens, you're going to go for the unions, okay? Whenever you end up thinking that this and this happens, A and B happens, so it's A intersection B. A or B happens, A union B, okay? So it's possible that A occurs and C doesn't occur, or therefore union, C occurs and A doesn't occur. So this is the representation. At least one of A and C occur, that's A union C, okay? So I think that is all for this video. Next we shall be solving some practice problems to get a better hang of these set operations. I'll talk to you in the next video. Bye.